Tô ligando. Pode começar.
Welcome everyone to today's seminar. This week we have Janice Lee, who is an associate astronomer at Caltech in California, United States since 2017. She obtained her PhD from the University of Arizona in 2006 and later held a Hubble and a Carnegie postdoctoral fellowships at the Carnegie Observatories. In 2011, she became a member of the scientific staff of the Space Telescope Science Institute, and she currently serves on the executive committee for NASA, for the NASA Cosmic Origins Program Analysis Group. Her research focuses on constraining the physics that drive, regulate, and extinguish massive star formation across different galactic environments. And she'll be talking to us about her latest work on the PHANGS-HST survey. Janice, thank you so much for accepting our invitation. Please start when you're ready.
Okay, so hello everybody. Thanks to Anna and the department for the invitation today. I hope everyone is well despite the circumstances. It's great to see new strategies that your department is using during these really challenging times to keep the seminars running and to support the speaker interaction with young scientists. So I'm really glad to participate today and to be able to learn more about your virtual seminar strategies firsthand. And with that, I'll turn off my video just to make sure we don't overuse the bandwidth on my end so the talk can go smoothly. Okay, and I will share my screen. Okay, so the title of my talk is PHANGS-HST, Linking Stars and Gas Throughout the Scales of Star Formation. I'll be presenting initial results from our first year of this Hubble Space Telescope Treasury Program, and for which observations began last April. Our program is working on connecting the basic units of star formation. And what I mean by basic units is our stellar associations and star clusters as resolved by HST. And we're doing this in a diversity of nearby galaxies, and then connecting them to the giant molecular clouds as mapped by ALMA. But first, let me take a step back and talk about why it's important to link stars and gas throughout the scales of star formation. And what does this even mean when I refer to the scales of star formation? Now, ultimately, a major goal of astrophysics is to be able to answer the basic question, how do stars form from gas? But as simple as the question can be posed and it sounds, we don't yet have a full predictive theory of star formation. Why? It's because ultimately it isn't as simple as studying individual molecular clouds on parsec scales to understand how they form clumps, protostellar cores, disks, and then finally stars and their attendant planetary systems. It's not as simple as this one picture because stars don't form in isolation. They form in a clustered manner, and moreover, they form within the context of galaxies. Star formation not only converts gas into planetary systems, but the process depletes galaxies of gas and feeds back metals, energy, and momentum into the ISM. And that energy, that feedback might reach the halos of galaxies and even beyond. The simulation you're seeing here is from FIRE, Feedback in Realistic Environments, the suite of code that they use to finally incorporate elements of feedback into hydrodynamic simulations. Here you're seeing a Milky Way mass galaxy, and it's illustrating how the gas responds to different sources of feedback from massive stars on small, and as you're seeing now, on large scales. And in turn, this feedback, together with galactic scale inflows and the dynamics of the galaxies, impacts the state of the gas and then the future of star formation. Now, we gradually learn from decades of observations across the electromagnetic spectrum, from the radio to the X-ray, that the mechanisms that drive, that regulate, that extinguish star formation in galaxies, they operate together over this vast range of stellar, interstellar, galactic, and even circumgalactic scales. And that's what makes the problem very difficult. Astronomy has divided itself into different groups, studying all of these processes separately. And oftentimes this is out of necessity, since specialized techniques and even different galaxy samples, different kinds of observations are required to study each of these processes in detail. And the division and the specialization, it's not only true for observations, but it's also true on the simulation and theory side. So to make progress and to inform the development of a unified theory of star formation, to even be able to understand the physical underpinnings of many of the scaling relationships for galaxies, well-known scaling relationships like the Kennicutt-Schmidt law, what we need to do is to have systematic observations spanning all of these spatial scales, all phases of the star formation cycle over the full range of galactic environments, because it's this interplay that results in the evolution of star formation in galaxies. And this is what our PHANGS program is trying to take a step forward in the volume of the universe, where we can resolve the basic units of star formation. And I'll refer to those again and again through the talk. Stars, star clusters, and giant molecular clouds. We're taking inventories of these populations throughout the disks of not just one galaxy or a few galaxies, but a full range of nearby galaxies, and using them to characterize the star formation parameters, as I'll now describe in more detail. And so in this part of the talk, I'll give an overview of the PHANGS-HST program, our greater PHANGS collaboration, and focus on some more specific scientific goals. The color composite that you see here in the background was produced by the amazing Judy Schmidt. It was based on our WIF-C3 images of NGC 2835. And this image will be released as the ESA Hubble Picture of the Week in a couple of weeks. So to reiterate, with PHANGS-HST, what we seek to do is to build the first astronomical atlas to systematically chart the evolutionary cycle between gas and stars and the fundamental units of star formation through a diversity of galactic environments in the local universe. Our sample contains 39 nearby galaxies, and all of these galaxies have CO 2:1 mapping from the PHANGS ALMA Large Program. We're using HST to image the same areas that ALMA imaged within the disk in 5 bands from the near UV to the I band. We also take the opportunity simultaneously to obtain V and I image in so-called parallel mode. Now, with these data, our visiting graduate student fellow at IPAC, Deep Anand from the University of Hawaii, who is doing his PhD thesis with Brent Tully. Deep has worked with our group to derive distances based on the apparent brightness of the tip of the red giant branch, which is used as a standard candle. So here's an example of a color magnitude diagram of individual red giant stars detected in the observations of the halo of the galaxy, which you can see here, it results in a distance of about 4 megaparsecs. So in this work with this incidental parallel observation, we now have these tip of the red giant branch distances to 11 galaxies, 5 of these represent the first TRGB distances for those galaxies, and 8 of these represent the best available distances. These kinds of distance measurements are incredibly important for a nearby galaxy sample because we cannot simply use the redshift to compute the distance due to peculiar velocities. And those can be comparable to the recessional velocities, again, for these nearby galaxies. And of course, we need the distances to derive all sorts of physical parameters. So back to the 5-band HST imaging of the disk, an example of what you see here. These data, combined with the ALMA maps, will allow us to construct a joint catalog of almost 100,000 star clusters, associations, and molecular clouds. What do these observations buy us in terms of resolution and depth? The HST imaging has a pixel scale of 0.04 arcsecond per pixel. That results in a resolution of about 1 to 5 parsecs for the distances of the galaxies in our sample. Now, this resolution, this high resolution, is required for identifying the basic units of young clusters and associations. And these the integration times that we use allow us to probe down to masses of about 10 to the 4th solar masses for young single-aged population. So young meaning younger than 100 million years. On the ALMA side, our maps are a combination of total power observations, 12 and 7 meter array observations, and together they yield a resolution of 1 arcsecond at a fixed velocity resolution of 2.5 kilometers per second. Here we can probe giant molecular clouds down to about 80 parsecs in size and down to about 10 to the 5th solar masses. So again, stellar populations down to 10 to the 4th, while the gas down to 10 to the 5th. And so these relative mass limits of clouds and star clusters are reasonable if we think that there's a star formation efficiency of around 10%. Observations began last April, and this was the first galaxy on my intro slide for which we received HST data, NGC 1559. In the red is CO, green is an HST white light image, and blue represents the near UV and traces the youngest stars. You can see that the CO is an exquisite tracer of the dust lanes. And for the most part, the optical light from the young stars comes to us through sight lines that are free of gas. So what exactly do I mean when I use the term star cluster? Here I'm showing some examples of compact star clusters and associations. The objects are quite small, again, comparable to our resolution with HST. There are a few to several parsecs in terms of effective radii. The first column that you're seeing here shows a color composite spanning about 1 kiloparsec. The second column shows a zoom on the color composite to 50 parsecs. And the last 5 columns are images in the individual filters, near UV, U, B, V, and I bands. The objects with a single peak, like these first 2 examples here, are thought to be gravitationally bound, though there's some debate about that. And then why do we care about studying these objects that look like this? Why do we care about studying these individual units of star formation? Well, aside from being important to study as the objects that form at the densest peaks of the star formation hierarchy, clusters and associations are extremely useful because you can effectively characterize them as single-aged stellar populations. So you can imagine them as little clocks that are spread all over the galaxy with specific ages, and that allows us to use them to time the star formation cycle relative to other clouds or other structures in the galaxy. And here again are 10 examples of now young clusters and associations overlaid with the ALMA data in red. Again, this illustrates that the optical light generally comes to us through sight lines free of molecular gas. All these young populations are already exposed, and this can provide constraints on the timescale over which stars separate from the natal clouds from which they were born. The joint ALMA HST PHANGS dataset will allow us to probe all these questions. As I was just talking about timescales, can we measure the timescale to the onset of star formation in clouds, the period during which clouds are inactive, the destruction of clouds, the overall cloud lifetimes, all these things added together, and the removal of gas from young star clusters. It allows us to study the relationships between mass functions of star clusters and associations and how they're related to the mass functions of clouds. It'll allow us to ask what the implied star formation efficiencies or cluster formation efficiencies are when we compare the mass functions. And finally, we can characterize how star formation and gas are organized into multi-scale structures and how those spatial distributions evolve with time. Now, while there has been work on these questions until PHANGS, until our program, they've only been studied with data in selected individual galaxies, for example, Magellanic Clouds or M51. There has not been systematic study across a full range of galaxy environments of these questions. So PHANGS then obtained ALMA CO maps for a diverse set of 75 galaxies, which you see here. For observations with HST, we chose the 39 best suited for study of the resolved stellar populations. What does that mean? We choose the ones that are relatively face-on, avoid the galactic plane, and we also limit the sample to those that are sufficiently active. That means star formation rates greater than 0.3 solar masses per year, meaning star formation rates greater than the Large Magellanic Cloud. And that's to ensure that we have robust GMC populations for joint analysis. Observations are nearly complete. We had our last HST observation of the year actually last week, and now imaging for 40 out of 43 pointings have been successfully completed. There remain 3 fields that are scheduled for next year, and these really are just re-observations due to guiding failures that actually seem to have decreased considerably since 2018. If there are HST users in the audience, you know that HST had a gyro failure and went to safe mode, and then they were trying to do some recalibrations, and there were a lot of failed observations, but seems to have gone back to a more normal state where observations are succeeding, so that's a good sign. With this diverse sample of star-forming galaxies, we'll then be able to probe how all these characteristics of cluster and cloud populations vary with galactic properties, larger scale galactic properties over the disk, averaged over the disk, such as ISM phase balance, stellar mass, gas mass, star formation rate, surface densities, metallicities, and the presence of dynamical features, rings, bars, and spiral arms. And in fact, there was this program, a precursor program called HST Legis, which has begun to answer some of these questions for the resolved stellar populations. And so I'll quickly highlight a couple of those results. But first, what is this HST Legis program? Legis, the Legacy Extragalactic UV Survey, also obtained 5-band HST imaging. But they did it for a sample of galaxies in both the north and the south, not just the ones accessible to ALMA, and ones that are closer, within about 11 megaparsecs. And this was to enable not only studies of clusters, but also to reconstruct star formation histories from resolved stars within the disk. So they needed to stay closer in order to resolve the stars. So as a consequence, the sample is really weighted to, as you can see from this diagram, towards lower mass. Mass is on the x-axis, star formation rate is on the y-axis. LEGIS is weighted towards lower mass, less active galaxies as compared with the Sloan Digital Sky Survey, which you see in gray, and with PHANGS in red. And of course, this is called the star forming main sequence. Now, with LEGIS, Dave Cook and I have studied 23 dwarf and irregular galaxies to investigate whether the fraction of stars formed in compact clusters, plotted on the y-axis, depends on galactic properties, such as the star formation rate density, as you see on the x-axis, when averaged over the disk. So it might be expected that, as previous work has shown, that the higher the star formation rate and gas density, the higher the cluster formation rate will be. So this has consequences for the so-called mode of star formation as a function of cosmic time and the formation of bound objects that survive to be globular clusters in the present day. But however, we actually don't find with our sample that there's a dependence of the cluster formation efficiency as a function of the star formation rate surface density. And the key here is that instead of mixing and matching different cluster populations of different ages, we ensured that clusters of the same ages are studied across all galaxies. And each individual point here, represents an individual galaxy. So the fraction of stars in clusters decreases from 25% for the youngest objects, less than 10 million years old, to about 5% when considering older clusters with ages between 10 and 100 million years. You can see again that there are no real trends here. They're pretty much flat as a function of sigma SFR, the star formation rate surface density. Also with LEGIS, graduate student Stephen Hatton has derived constraints on the time scale for gas clearing from young clusters. Now this is based on 16 LEGIS galaxies, those which also have H-alpha narrowband imaging with Hubble. As part of his PhD thesis, Stephen has classified the H2 region morphologies around young star clusters, and then he studied the SED fit ages of those parent clusters with different H2 region morphologies. Now, this is one application which uses clusters as clocks, as I was saying before, to time the star formation cycle. And here we find that the age distribution of clusters with concentrated H2 regions, look like this, are the same as those which have a partially exposed morphology, look like this. And the median age of those distributions is about 2 million years. What this implies is that the clearing timescales are shorter the uncertainties in our age determinations, which are less than 1 million years about, and that also it's not just feedback from supernovae that's important. Supernovae begin at about 3 million years. So if the median age from which this morphology occurs is about 2 million years, it implies that other feedback mechanisms such as radiation, pressure, and stellar winds must also play important roles. Given these and the many other results from LEGIS, and even considering the GOALS program, the Great Observatory's All-Sky LIRG program, which is systematically studying the most actively star-forming galaxies in the local universe, one might ask, why do we need PHANGS? Why do we need another imaging survey of nearby galaxies with HST? So as I was describing before, PHANGS is needed to complete coverage of this star formation sequence. And moreover, it lies in a sweet spot in distance, in volume. And this is the volume where HST can still resolve star clusters and associations, while at the same time, ALMA can detect the molecular clouds. And both observatories can efficiently image the whole extent of the star-forming disk in one or a few pointings in a reasonable amount of time. And here are the folks who have been hard at work on the PHANGS-HST data over the last year. We have 3 outstanding young scientists in the job market this year. Jordan Turner, PhD student with Danny Dale at the University of Wyoming. Post on Kirsten Larson at Caltech IPAC in our group. And again, Deep Anand, who was our recent IPAC visiting graduate student fellow. And we are a part of an even larger collaboration led by Ava Schöner, Adam Leroy, Eric Rosolowski, Eric Emslem, and Guillermo Blanc. PHANGS now involves 60 scientists in 4 continents, which is managed by a steering committee and organized into 10 science and data working groups. In addition to the ALMA and HST data for the sample, PHANGS has also obtained VLT-MUSE data for 19 galaxies, and that further enables joint studies with the optical emission line tracers of the warm ionized gas. Now, this speaks back to the difficulty of the challenges of doing this kind of work, this intersectional work. This project is really only possible through a collaboration of collaborations. We've brought together 3 distinct research networks with specialized expertise on radio observations in cold gas, integral field spectroscopy and nebular emission, and from my group, space-based UV optical IR imaging and resolved telepopulations. And so now on to a quick survey of some initial results from the first year of the PHANGS program. Here we have another stunning color composite, again from Judy Schmidt, this time of the flocculent spiral galaxy NGC 2775. And this was released as the ESA Hubble Picture of the Week at the end of June. First, I'll show results based on a proof of concept study. And this is to use convolutional neural networks to classify star cluster candidate morphologies. This was a separate collaboration with machine learning experts at the National Center for Supercomputing Applications at the University of Illinois. And the takeaway here is that the so-called deep transfer learning techniques of training neural networks can produce models which provide classifications with accuracies comparable to humans. Why do we care about training neural networks? This seems so different from the physics and astrophysics that I was just talking about. Well, it's motivated by the fact that human visual inspection and classification of the source lists of cluster candidates has been one of the major limiting steps in previous star cluster studies. And what we want to do here is to automate the process and expedite the science. We want to differentiate between these 3 classes of compact clusters, which I showed before, and associations in this last row, and then distinguish them from automatically detected sources that are not clusters at all, these artifacts, background galaxies, and stars. And these can be over 50% of the candidate sample. And each sample for each galaxy is on the order of a few thousand objects. Now, previously, all of this work was done by graduate students, postdocs, and a few senior astronomers, visually looking at each of these images to take away the artifacts and then to classify into these 3 morphological types. Again, the first 2 are considered to be likely gravitationally bound objects. Because the sources that have human classifications thus far that can be used for training networks are relatively small compared to the sizes of samples used by data scientists, we use this technique called deep transfer learning. So instead of training a neural network from scratch, we use pre-trained networks on massive data sets of actually everyday images, nothing to do with the night sky. And this allows the network to recognize corners, shapes, illuminations, very general features. And then we only train the inner layers of the network on the HST imaging. We experiment with different architectures, different training sets, and the sizes of the images used for training, and then expose the networks to new data from PHANGS. The results of the neural network classifications are typically presented in these so-called confusion matrices, with the true label on one axis, true label determined by the human and the predicted label determined by the machine, and the prediction accuracies can be read off the diagonal. The punchline here is that we can predict the classifications to the class 1 symmetric single peak clusters with the highest accuracy, about 70%, with the remaining classes about 40 to 50%, at the 40 to 50%, up to 70% levels for the artifacts. And now while these accuracies may seem low, they're actually similar to the consistency in human classifications. So in principle, we can use them, but with great care, to automate the classification and again, to expedite science. I'll skip over that. But clearly, we do want to try to improve these accuracies, in part by standardizing the human classifications and training sets. But we also want to know whether we can do better with other methods. Neural networks are somewhat of a black box. So, can we figure out another way of doing this that also provides insight into the physical nature of the morphological types? And so this is the topic of innovative work being carried out by postdoc Sinan Digar at Caltech. So Sinan is applying quantitative morphological metrics that were initially developed for galaxy studies, like the concentration, asymmetry, index CAS, that was, I think, developed by one of the speakers that will be giving a talk in the next few weeks for you, and also the Gini M20 parameter. And he's applying these quantitative morphological parameters to the clusters now instead of galaxies. And in his initial work, he's using a sample of bright, relatively isolated clusters in the 3 classes that I just described across 15 PHANGS galaxies. What you see here is a U-B-V-I color diagram, and this is a standard tool for studying single-aged populations. The track shows the evolution of a single-age solar metallicity population from Brunelswald and Charlot, 2003. The first thing to notice is that the cluster colors do fall along the track, and this again indicates that the objects can be described as single-aged populations. The single peak symmetric objects, class 1 in the gray, they tend to be old globular clusters. The class 2 single peak asymmetric objects are purple and span the full age range, while the multi-peaked associations are blue and tend to be young. So what Sinan has shown is that when the M20 morphological parameter, which I won't discuss in detail, is added to the color diagram, there's a projection of the plane which distinguishes the cluster types. And he'll be trying to understand the utility of this more in his future work, as well as other morphological parameters, and coupling that to other physical parameters from the ALMA data. And so finally for today, I'll mention more innovative work, here led by Kirsten Larson. And she is applying a watershed algorithm to a point source catalog to more robustly identify single-aged associations. Now, these are the objects with multiple peaks as opposed to single peak. And these are the ones that also tend to be young. So the compact clusters that we've been focused on for most of this talk represents only about a quarter of the overall star formation. If you remember the plots of the star formation, the cluster formation efficiency, it's only a quarter. So here we're trying to identify the more loosely bound structures associated with the majority of star formation in the galaxy. And obviously a complete inventory of the star formation is critical when we want to perform joint analysis with the molecular clouds. And the results from her pilot study of 2 galaxies, here you see one of them, NGC 1566, The two galaxies in the study have distinct morphologies and span the distance range of PHANGS galaxies. It shows that the technique actually works. Here in the background is an H alpha image of 1566, and overplotted are the associations that Kirsten has identified with the watershed algorithm. The colors represent different age ranges, and so it's very encouraging that the youngest structures that you see in blue, less than 3 million years old, actually do trace the H2 regions very closely. And even the ones that are slightly older, 3 to 5 million year old structures, they're offset from the H2 regions, from the spiral arms. And the older structures here, all just color-coded in red, all the associations older than 60 million years, which you do not expect to give rise to ionized emission, nebular emission. They're just widely distributed. Kirsten is also taking our group's first look at the cross-correlation between these young associations in the molecular clouds. And so here's 1566 again, and now just showing all the associations associated with NUV flux overplotted on the CO map. Okay, so this brings me to the end of the initial results that I wanted to share today. I know it was a lot, and it tried to weave an integrated, synthesize a picture of it, but to go back and summarize to see how all these things connect together. Our conclusions, first from the precursor LEGIS survey, is that we don't see a dependence of a fraction of stars formed in compact clusters on the star formation density over a couple of dozen galaxies. So that speaks to how small scale star formation might depend on global properties of the disk. Again, with LEGIS, we've shown that the onset of gas clearing prior is less than 3 million years, which is prior to the explosion of supernovae. And this indicates that radiation pressure and stellar winds are important sources of feedback for clearing the natal gas. And then from our first year of, a couple of results from the first year of PHANGS-HST. Of course, to study star clusters, we first need to detect and classify them. And again, this has been a limiting step in prior surveys. So to begin, we're experimenting with different techniques, such as using neural networks with deep transfer learning and quantitative morphologies, and they both show promise for automating classifications of these tens of thousands of sources. And then finally, because compact clusters really only represent the tip of the iceberg of star formation, we need to identify the rest of the stellar associations corresponding to the majority of star formation, and we're trying to do this with a watershed algorithm. We show that it's effectively able to group stars into single age structures, and this will be essential for comparison with the molecular clouds and deriving the parameters that I spoke about earlier. And there will be much more to come in years 2 and 3 of PHANGS-HST, much more astrophysics as when we get past these initial steps. Thank you very much.
Thank you very much for your talk, Janice. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them in our YouTube channel, and our speaker will try to answer them later. Goodbye.